worked with Akamai Technologies in order to create a resource timing analysis tool. My name is Rita.
Ian.
Andrew.
I'm Jason.
I'm Gabe. Edward. Kevin. I'm Rainer.
All right, so let's get started.
So Akamai is a content delivery network, or CDN. Their product is actually a set of features which help speed up page loads. So their position with regard to the server-client relationship is basically the server here is like your AWS server, the server in your closet and whatnot, and the client is here. And they're the person who's actually viewing the web page. And Akamai sits in between them, which allows them to apply certain features to improve the page load. And we're going to be going into those features specifically later. So the problem statement is that right now, when Akamai wants to assess features to provide to a client, they basically have a specialist sit down with them, and based on intuition and looking at the code of the page, decide which features will best improve the performance. The issue is this is not programmatically verifiable. You can't say, oh, this feature improved the page this much, and you shouldn't use this feature because it'll only improve the performance, 1 or 2%. So we set out to build a tool that would allow this to be programmatically verifiable. Our approach was threefold. We started off by analyzing and unpacking the resource timing data provided by Akamai. Then we created predictive models to find the patterns in this data and allow us to suggest features. And then we created tools to test and verify our models and determine actually how much performance could be gained by applying any individual feature.
Okay, so for the purpose of testing our models, we designed and implemented a verification pipeline. In order to simulate and tweak the loading of a web page, we use a base page generator, an origin simulator, Facebook's open source augmented traffic control, and our goat herder, which is a client simulator. Additionally, we needed to be able to observe the changes that our algorithms made, so we generated visual representations of the page data, which will be referred to as a waterfall chart. Also, in order to ensure that we weren't creating tools that would only work on one developer's workstation, we created a uniform environment using Vagrant, VMware, VirtualBox, and LXC. This is the pipeline I was talking about. We're going to be taking you through each of the tools and then talking about the features. The first stage of the pipeline is the model application. The tool used mainly in that is the base page generator. Okay, so a base page is the first resource page returned from a request. It's usually an HTML page, and it references all other resources on a page. What our generator does is it takes the results of a dependency tree generator provided by Akamai or resource timing data in order to create a base page representation of an Akamai's customer's web page. This is used with the origin simulator with adjustable parameters, and it also works with ATC, which is the augmented traffic control, and a client simulator to alter and observe page loads. The next part of our pipeline is the origin client interaction simulation. The first tool we're going to be talking about is the origin simulator.
The origin simulator is an HTTP web server written in Go for base pages and resources generated by the base page generator. The origin simulator is able to insert delays before sending a response in order to simulate origin think time. It can also make the same resource available at multiple different URIs in order to simplify base page generation and to model optimizations such as object versioning. Traffic to the origin simulator is routed through ATC in order to simulate real-world network conditions. This right here is a screenshot of a base page loaded from the origin simulator through ATC. We had a nifty animation, but apparently that's not working today. This right here are two pictures of my goat.
Hence the goat herder. Okay, so the next part of the origin client interaction simulator
is the augmented traffic control, or ATC. ATC is a proxy that sits in between our origin and client simulators, allowing us to control real-world network conditions, such as download and upload speed, latency, and packet loss.
Okay. Next is the goat herder, which is our client simulator.
The client simulator, or goat herder, is a tool to collect resource timing data from page loads. The goat herder is based on the Selenium browser automation framework to allow us to use a real web browser. The goat herder outputs the hybrid tab-separated JSON format required by the waterfall chart generator.
And you can see an example of that. Okay, the next stage in the pipeline is the graphical representation. So we're going to talk about the waterfall generator.
So the waterfall generator is a
control script provided by Akamai that processes resource timing data into a visual format. The different resources on a page are represented by horizontal bars, where the length of the bar is corresponding to the length of the object's load. The different colors within the bars signify different key points in the object's loading process. For example, one color signifies the amount of time spent waiting for the first byte of an object to be received, while the following color might signify the amount of time spent downloading the remaining bytes of that object. We use the waterfall charts to first build an intuitive understanding of how objects load within a page for model development, and also as a visual comparison to assess how well our models perform before and after application. The more horizontally compacted the waterfall, the faster the page load, signifying a more optimized page.
Okay, so now we're going to get to the meat of the project, which is the features and the models we came up with. We're going to be talking about object versioning, manipulating TCP parameters, edge start, domain sharding, image resize and format conversion, and cookieless domains.
So the problem object versioning aims to solve is that of objects frequently updated in place. That is, objects updated using the same name. Normally when a browser visits a page, it attempts to cache objects on that page so it doesn't need to load them on subsequent visits. Frequently updated objects, however, are not allowed to live in the cache for long, because if the object is updated on the page, but an old version is present in the cache, the browser will load the old version, which is clearly incorrect. To address this problem, we detect pages that have many frequently updated objects and apply object version. Object versioning identifies when an object has been changed and rewrites the base page to refer to it by a new name, derived from the contents of the object to guarantee uniqueness. This renamed object is allowed to live in the cache indefinitely, so that if the object hasn't been changed, it will be guaranteed to be in the cache. But if the object has changed, it will be referred to by a new name, which the cache does not know, forcing the browser to load it anew, eliminating the confusion from before.
So for those of you that don't know, TCP stands for Transmission Control Protocol. When a client connects to a page, there's what is known as the initial congestion window. This window dictates the total number of packets that can be sent through the connection at one time. For some pages, if this initial window is too small, multiple round trips are going to be required between the client and the origin. So for some pages, increasing this initial window will improve performance by reducing the amount of trips needed between the two servers. So EdgeStart is a feature of Akamai's that we worked on finding candidates for. It's a feature that is targeted particularly at web pages with a lot of dynamic content. Objects that are dynamic change frequently, so they cannot be cached in the same way as static content. The way EdgeStart works is an initial client will connect to a server that has a lot of dynamic content on it. The Edge server will snoop this request and realize that it cannot cache these objects. When another user, though, connects to the same page, the Edge server will realize that it has cached the static elements of the page, such as HTML, CSS, and JavaScript, and can send that to the user concurrently while fetching the dynamic content.
Domain sharding is an optimization that circumvents the per-domain connection limits imposed by browsers. Domain sharding works by rewriting the base page to distribute objects across multiple subdomains, therefore increasing the number of simultaneous connections opened by the browser. Domain sharding is most helpful for connections and for pages with lots of resources or clients connecting through congested networks.
So image resizing and format conversion. The problem here is that a website might be trying to serve an image that's too large and going to slow down a page load for a screen that's much too small to even view the content on this image. To solve this problem, our algorithm was we computed a time delta factor across all images. And host names that had many large time delta images were candidates for this. The way we tested this was we resized the images and reloaded the whole page through our pipeline and determined the improvement we studied.
Cookieless domains is an optimization that prevents the sending of the same cookie data with every single request on a page load. Cookieless domain works by rewriting the base page to shift resources off of the root domain onto subdomains without associated cookies. Cookieless domains is most helpful for clients with slow upload speeds.
Okay, so finally, after the resource timing data is fed through our pipeline and all of our models are applied to it, we get a new waterfall chart. Here's an example of a waterfall chart before and after domain sharding. On the left, you can see we can only load 6 resources at one time, so all subsequent groups of resources have to wait for the previous group to finish before they can start. On the right-hand side, you can see that all 24 items are loaded at the same time. You can also tell that there's an improvement because, as it was said before, it's more horizontally compressed, therefore it's a faster load time. So, in conclusion, we were able to create a tool for analyzing resource timing data for a given page in order to decrease load time and increase efficiency. To do so, we created models for the features, we analyzed the resource timing data using said models, we identified patterns in the resource timing data that could be optimized by applying a feature, and we simulated new page loads and verified performance benefits. Are there any questions? Okay.
Thank you.
Yes. Yeah.
Just one question is, has this tool been demoed in Akamai? Have you got any feedback from the sponsor?
Not yet. We have plans to do that soon. There's a few finalizations we need in the actual coming together of a full toolkit. Right now, it's separate tools that just need to be worked together.
Thank you.
Okay? Thank you.